Hi, welcome back to Honors Topics in Physics. Today we are covering Newton's third law. For every action there's an equal and opposite reaction. I normally like to start out this discussion with putting two students on these wheeled little carts and then having them push off of each other patty cake style and having them both, you would see them both go backwards. And it would not be very surprising because, you know, the one person pushed the person to the left and the other person pushed the person to the right. So they pushed each other and they both moved off. Then what I do is I have one person turn around. So now they're facing this way and I have this person push off. Okay, and the question is who's going to move backward now, because this person A and this person B. Person B is going to push person A to the left, so we know person A is going to go to the left. What about person B? Are they going to move? They are going to move. And the thing is that even though person A didn't consciously push person B to the right, okay, Newton's third law is an inescapable consequence of reality. That when B contacted A, B pushed A pushed B backwards, and that's Newton's third law. They both students had a force acting on them. And this leads to some interesting things. What force accelerates a car forward? We know is the force of friction between the tires and the road, but something interesting happens there. But how does the shuttle take off? It's not pushing off of the ground once it. It's not pushing off the ground. So how does it take off? How do they work in space? So picture you're on a boat and you're standing and you want to jump to this dock. Okay, you're going to jump. In order for you to make it to the dock, the boat has got to exert a force on you, and the boat has got to push you to the right. So there must be a normal force on the person by the boat. Okay, but when you do that, the boat's going to go the other direction. Okay, that's because there was an equal and opposite force acting on the boat by the person. Okay, so there was a force on you by the boat to the right. Okay, and there was a force on the boat by you to the left. Okay, the boat pushed you to the right, and you pushed the boat to the left. This is Newton's third law. These forces are equal in magnitude and opposite in direction. Okay. You cannot touch something without it touching you. That's another way of stating this law. Okay, another way of saying this is that they come in pairs. Forces always come in pairs. There's no such thing as an isolated force. Forces always come in pairs on different objects. Okay, and this is not something. This is not a conscious push or pull. When you push on the wall pushes back on you. The wall isn't trying to push back on you. It's just because you're in contact. But keep in mind, these Newton third law forces, or action-reaction forces, they are on different objects. Okay. So some other examples of Newton's third law. Let's say you're playing soccer and somebody kicks a soccer ball and wham, it hits you right in the nose. Okay. If you're the player, you know that there's a force on your face because you feel it. Okay, and your head maybe gets knocked back some. Okay, so Newton's third law says if there was a force on the face, there's got to be a force, another force. There's got to be an action and a reaction force, or an interaction force. And if there's a force on the face by the ball, there's a force on the ball by the face. All you do is flip the feeler in the dealer. Okay, so there's a force on the face by the ball, and there's a force on the ball by the face. Okay, so, and they are equal in magnitude and opposite in direction. The ball pushes the person's face to the left. The person's face pushes the ball to the right. Okay, and again, this is not a conscious push. This is just an inescapable consequence of existence. Do these forces cancel one another out because they're equal and opposite? Your first reaction might be yes, they must, because they're equal and opposite. They must cancel out. But they do not. I don't know if anyone knows why these forces would not cancel out. Well, one force is on the ball, the other force is on the person. In order to cancel out, they have to be on the same object. So these forces would not cancel out because they are on different objects. Okay? So, for example, if I were to apply a 5 newtons to the right and 5 newtons to the left on the same person, okay, that person would just stay there. Those forces would cancel. However, if these people push off, these girls push off, and there's 5 newtons of force on the left girl to the left, and there's 5 newtons of force on her to the right, they're both going to fly off to in opposite directions. Okay? If forces are on different objects, they can't cancel one another out. Okay? Some common scenarios. So if you catch a ball, okay, there's a force on the with a mitt, okay, or your hand. Let's say you catch it with your hand. There's a force on the hand by the ball, and if the ball was thrown hard, you know that there was a force on your hand because the hand might sting a little bit. Okay. There was also an equal and opposite force acting on the ball, and you know that there was a force on the ball because it decelerated, it slowed down, it came to a stop. So force on the hand, ouch, force on the ball comes to a stop. Okay. Hammer and nail. When you hit a hammer, when you hit a nail with a hammer, there's a force on the nail because the nail gets driven in, okay, and there's also a force on the hammer, okay, because the hammer was swinging and it comes to a rest on the nail. Which has the greater force on it, the hammer or the nail? Did I trick you? Same. Newton's at. These are opposite, equal and opposite forces. When you accelerate a car, okay, so this is the car, and this is the planet Earth, and not to scale. That would be a very ginormous car or a small planet, either one, but not to scale. So there is a force of friction when you accelerate between your tires and the road. Oh, it's going to erase now. So what accelerates your car is the force of friction on the car, which is really the tires, on the car by the road, okay, by the earth. Okay, and that accelerates you forward. Newton's third law says that there has to be an equal and opposite force, okay, also a force of friction on the earth by the tires, okay, or on the earth by the car. So just like when you jumped off that boat and you push the boat back, when you accelerate your car, you push why is the force so much more noticeable on the car than the earth? Okay, you don't go around changing the time of day when you accelerate your car. Well, even though there are identical forces acting on the earth and on the car, the earth has so much more mass that it's not as affected. It's got so much more inertia. So there's a much bigger effect or much bigger acceleration on the car. Okay, when you throw a ball up in the air and it's falling back towards the earth, there is a force of gravity, okay, on the ball. That's a good-looking G for drawing with the mouse. There's a force of gravity on the ball by the earth down. Okay? Newton's third law says there's got to be an equal and opposite force, okay, with the feeler and dealer flipped. So there's got to be a force of gravity on the earth by the ball. So when the earth pulls the ball down, the ball pulls the earth up. Okay, strange enough to think about, but it is true. Okay, which has the greater force on it, the ball or the earth? Okay, same. Newton's third law, forces are equal and opposite. So then we could keep coming up with these forces all day, because every single force that exists or ever has existed always has a pair. So you could come up with these examples. So picture a cannon firing a cannonball. So what is the action-reaction pair here? Well, the action, we might say, is the cannon pushing the ball to the right. Okay, the reaction might be the ball pushing the cannon to the left. Okay, that's known as recoil. When things fire, the projectile goes forward and the device tends to go backwards. Now, who feels the greater force, the cannon or the ball? Same. I better not still be tricking you. Okay. Now, does that mean they both speed up the same? They both accelerate the same rate? No. The one that accelerates more is the cannonball because it has less mass. Okay. Let's say that you're off in space and you didn't tie off to the space shuttle or the International Space Station, whatever you're happen to be working on. All you have with you is a hammer, and you're floating away from the space shuttle. What do? Hotshot, what do you do? Well, what I would do is I would throw the hammer away from the space shuttle as hard as I could, because when I pushed the hammer to the left, okay, the hammer would push me to the right, and I'd move towards the space shuttle. Okay, it would exert an equal and opposite force on me. Okay, a little bit on how rockets work. How does the space shuttle work while we're on the topic of it? Well, if we think back to if you've ever shot a gun, okay, think back to the cannon we just talked about. When you fire a projectile forward, okay, that gun gets pushed backwards. It kicks. It's called recoil. I have a video of recoil here, and this is Newton's third law in action. I had a video, and so this is the video. You can see he's holding that rifle very poorly. Let's rewind that. So he's getting ready. He knows this is going to hurt. So again, that's Newton's third law. In order for the gun to push the bullet forward, the bullet has to push the gun backwards. That's just that's how reality works. So we can think of rockets. They don't shoot bullets. They shoot this exhaust gas one way. Let's say, according to this picture, they're shooting the exhaust gas to the right. This machine gun is shooting bullets to the right, and every time it shoots a bullet to the right, the gun gets pushed to the left, so it would be accelerating to the left. So this rocket is shooting this exhaust gas to the right, and just like the gun itself, it's recoiling, it's to the left. So we can picture this when rockets take off, they've got a fuel and an oxidizer. And they combine these two, if we can think of them as fuel and oxidizer bullets, when they ignite, they expand, and they shoot out this exhaust nozzle, which is supposed to be this V shape here, and when they do so, they push off against the shuttle the opposite way the exhaust is going. So forces on an airplane. We've already talked about weight. We haven't really talked about drag, but I think we've talked a little bit about wind resistance, so I guess we've covered drag a little bit. What causes thrust and lift? More specifically, I want to talk about lift. How does a wing generate lift? Well, there's two ways that a wing generates lift. One is that when the wing goes through the air, it doesn't go through the air perfectly flat. It's tilted up a little bit. So this is supposed to be the cross-section of a wing. Like if you were to saw a wing in half and look at its cross section, and this is supposed to be it flying through the air, and this is the air coming at it, the air molecules. So anyway, so when the wing hits the air, it pushes the air down. Okay, and when the wing pushes the air down, Newton's third law says the air pushes the wing up. Okay, and that's one way that an airplane generates lift. The other has to do with the curvature of this shape. This is known as an airfoil, and Bernoulli's law. I'll let you look that up if you're interested in how does an airfoil generate lift. Okay, so we've got a person who's on the floor and they're stationary. What are the forces acting on the person standing on the floor? Well, we've got the force of gravity down, and we've got a normal force up, okay, from the floor. Okay, are these forces interaction pairs? So these forces action-reaction pairs. the force of gravity on the person down and the force of the normal force on the person up? No. Okay. These forces cancel, and they're both on the same object. Newton's third law forces are on different objects. So they're part of two separate interaction pairs. There's a force of gravity on the person by the earth down. Okay, the interaction pair, the reaction to that force is there's a force of gravity on the earth by the person up. Okay, so when the earth pulls the person down, the person pulls the earth up. Okay, the normal force, there's a normal force on the person by the earth, okay, pushing the person up. Okay, there's a normal force on the earth by the person pushing the earth down. Okay, those are two separate action-reaction forces or pairs. Okay, and lastly, just about done here. Let's say we've got a little kid and a big kid, and they push off of each other real hard. Who feels the greater force, the little kid or the big kid? Okay. No. Okay, if you said little kid, you're not catching on. It's the Newton's third law says they both feel an equal and opposite force. Okay, now who accelerates more? Now it's the little kid. The little kid is going to accelerate more even with the same force because he's got less mass. So now let's say that they had a rope in between them, and this time they yank. Who's going to feel the greater force, the little kid or the big kid? Okay, it's going to be the same. The rope isn't going to change anything. They're both going to experience the same force, but the little kid is going to accelerate more quickly. The rope just transfers that force. Okay, and that is it for the day.